Lesson 23.1, Probability Distributions. Essential question: what is a probability distribution for a discrete random variable, and how can it be displayed? Let's see, a probability distribution. I think what I need to do here is I need to get me some white space. All right. So, a probability distribution shows the probability is associated with each possible value of the random variable. It can be displayed using a histogram with bars centered on the possible values and having a height equal to the probability for that value. All right. So the essential question: what is a probability distribution for a discrete random variable, and how can it be displayed? Well, it's associated with each possible value of the random variable and can be displayed with a histogram centered on the possible values and having a height equal to the probability for that value. Using simulation to obtain an empirical probability distribution. A random variable is a variable whose value is determined by the outcome of a probability experiment. For example, when you roll a number cube, you can use the random variable x to represent the number you roll. The possible values of x are 1, 2, 3, 4, 5, and 6. A probability distribution is a data distribution that gives the probabilities of the values of a random variable. A probability distribution can be represented by a histogram in which the values of the random variable, that is, the possible outcomes, are on the horizontal axis, and the probabilities are on the vertical axis. The probability distribution for rolling a number cube is shown. Notice that it is a uniform distribution. Okay, it's straight across there, 1/6 for each one. When the values of a random variable are discrete, as in the case for rolling a number cube, a histogram for the probability distribution typically shows bars that each have a width of 1 and are centered on a value of the variable. The area of each bar, therefore, equals the probability of the corresponding outcome, and the combined areas of the bars are the sum of the probabilities, which is 1. A cumulative probability is a probability that a random variable is less than or equal to a given value. You can find cumulative probabilities from a histogram by adding the areas of the bars for all outcomes less than or equal to a given value. Suppose you flip a coin 5 times in a row. Use a simulation to determine the probability distribution for the number of times you flip times the coin lands heads up. All right. When you flip a coin, the possible outcomes are heads or tails. Use a graphing calculator to generate the integers 0 and 1 randomly, associating each 0 with the tails and each 1 with heads. Okay. Remember, there's 2 sides to the coin. There are 2 sides to the coin. And if it's a typical coin, there's a 50% chance that it would be tails. And there's a 50% chance that it would be heads. Okay. To do this, so I'm going to show you how to do it in the Inspire. This is for the 83 and 84 right here. So let's go to our Inspire. Go to Calculate, Menu, 5 for Probability, 4 for Random, and then 2 for Integer. And we'll put in 0, 1. Enter. All right, so that gives us the heads. That gives us the heads. That gives us the tails. That gives us the heads. And that gives us the tails. So we got 1, 2, 3 heads and 2 tails. And that's for 5, right? Okay. Now press enter 5 times to generate a group, okay, of zeros and ones. This simulates one trial, that is, one set of 5 flips. Carry out 4 trials and record your results in the table. All right, I did that off the thing, just showing you how to, and this is what we got. Okay, 4 trials. And trial 1, I got 2 heads. Trial 2, I got 1. Trial 3, I got 2. Trial 4, I got 3. Okay. Report your results to your teacher in order to combine everyone's results. Use the combined class data to complete the table. To find the relative frequency for an outcome, divide the frequency of the outcome by the total number of trials in the class and round to the nearest hundredth. All right. Let's see. I have a total of 60 students, so we'll have between the two classes. And let's see, we got 5, 9, 18, 16, 7, and 5. Now let's see, 5 divided by 60 is 0.08, and we can try that in a calculator. 5 divide 60, control enter, and I got 0.08. All right, 0.08. Now I've already done this for all of these. 0.15, 0.30, 0.27, 0.12, and 0.08. Enter the outcomes 0 through 5 into your calculator as list 1 and relative frequencies as list 2. Make a histogram. Okay, let's see here. All right. Selecting the histogram. Okay, so let's see here. Let's move this up here like this. All right. Now, like I said, this is how to do it on 83 or an 84. I'll show you how to do it in the Inspire. Press on and then histogram, or excuse me, let's see, on and then the table or the spreadsheet, and we'll put heads. HEADS, and that was 0, 1, 2, 3, 4, and 5. All right. And then here we'll put frequency and FREQ. And frequency was 5, 9, 18, 16, 7, and 5. All right. And then over here, we'll put relative frequency. So we'll do REL and F for relative frequency. And we got 0.08, 0.15, 0.30, 0.27, 0.12, 0.08. Go back up in your data, and let's go to our graph where the bars are. Click on that, and then here we'll put heads on the bottom, number of heads. Now, over here, kind of highlight that a little bit, and then press Control Menu, and see where it says Add Y Summary List. Click on that, and then there we go. Relative frequency. Add summary list. Okay, so take a look at that. And if you'll notice, it kind of follows it's approximately normal. So we'll say here, the distribution is bounded. The distribution is bounded and has tails that are roughly symmetric. They're not perfectly symmetric, but they're roughly. So the distribution is approximately normal. So it is approximately normal. Discussion. If you flipped a coin 5 times and got 5 heads, would this cause you to question whether the coin is fair? Why or why not? Let's see here. The probability of getting 5 heads and 5 flips with a fair coin is very low. And let's look. Yeah, see, that's very low. So I might question whether I might question whether the coin is fair. Is fair because the probability of getting 5 heads in a row is very low. All right. Uh, it's not impossible, but it's very low. So it might not be a fair coin. Recall that a binomial experiment involves repeated trials where each trial has only two outcomes, success or failure. The probability of success on each trial is P, and the probability of failure on each trial is Q, which is 1 minus P. The binomial probability of R successes in n given trials is given by P of x equals R equals n choose R times P to the R times Q to the n minus R. Calculate all the theoretical probabilities for the given binomial experiment, then draw a histogram of the probability distribution. Observe its shape and use it to find the specified probabilities. All right, A binomial experiment consists of flipping a fair coin for 5 trials, where getting heads is considered a success. Find the probability of getting 3 or more heads and the probability of getting at least 1 head. To calculate the probabilities, set n equal to 5 and let R range from 0 to 5. In n choose R times P to the R times Q to the n minus R. Since the coin is fair, P equals 1/2 and Q equals 1/2. So how did they get this 1 over 32, 5 over 32, and so on? And I want to show you. All right, so we have 5 C 0 times 1/2 to the 0 times 1/2 to the 5. That's this one here. Okay, and we'll go to our calculator and let's see, new document. No, calculator. Menu 5, 3 for combinations, and then that's going to be, what was it, 5, comma 0, close parentheses, open parentheses, 1, control, divide, 2, close parentheses, caret, I gotta get outside of the parentheses. Caret 0 times open parentheses 1, control, divide, 2, close. I did it again. Close parentheses, caret 5. 1 over 32. Okay. So how did they get 1 or 5 over 32? So that's going to be 5 choose 1 times 1/2 to the 1 power and 1/2 to the 4th power. All right, let's do that. Menu 5, 3, 5, comma 1, close parentheses, times open parentheses, 1, control, divide, 2, get out from under there, close parentheses, caret 1, times open parentheses 1, control, divide 2, caret 4, and 5/30 seconds. And you can do that for the rest of them. But I wanted to show you how they did that. All right, so create a histogram. The distribution is mounded and has symmetric tails, so it is a normal distribution. The probability of getting 3 or more heads is, now 3 or more heads is a probability of 3 plus the probability of 4 plus the probability of 5. So it's 10 30 seconds plus 5 30 seconds plus 1 30 seconds, which is 16 30 seconds or 1/2. The probability of getting at least 1 heads is 1 minus the probability of getting no heads, or 1 minus 1 over 32, or 0.969. All right, B. A binomial experiment consists of flipping a biased coin for 5 trials where getting heads is considered a success. The coin lands heads up 75% of the time. Find the probability of getting 3 or more heads and the probability of getting at least 1 heads. All right, so let's do this. So P equals 0.75, Q equals 1 minus 0.75, or 0.25. All right, so we're going to get 0 heads, and I'm going to just write the formula down under there. We're doing 5 trials, so 5, choose 0, and that's going to be 0.75 to the 0, because we're not getting any heads here. Well, maybe it put 1/4 there. Okay, so we'll put 0.25 to the 5th power. All right, so let's try that. Menu 5, 3, and then 5, comma 0, close parentheses, times open parentheses 0.75, close parentheses, caret 0, and then times open parentheses 0.25, close parentheses, caret 5. And let's see, menu 2, 2. 1 over 1024. So this is 1 over 1024. For one, let me get a different color. For 1, that's going to be 5, choose 1, 0.75 times 0.25. That's going to be to the 1st power, and that's going to be to the 4th power. All right, and we'll do that in the calculator as well. Menu 5, 3, and 5, comma 1, close parentheses, times open parentheses 0.75, close parentheses, caret 1, times open parentheses 0.25, close parentheses, caret 4, and let's convert that. That didn't do it. Menu 2, 2. 15 over 1024. So that's going to be 15 over 1024. And you can do that for the rest of them. Change colors here. 2 was 90 over 1024. 3 was 270 over 1024. 4 was 405 over 1024. And 5 was 243 over 1024. Okay. Now we need to do our histogram. And let's do our histogram. So 0 was 1 over 1,024. So that's going to be, let's just draw a little line right there. That's 1. That's 1. 1 over 1,024. Probability of 1 was 15. And that's not going to be much higher. Not much higher. We'll fill that in. And the probability of 2 was 15, was 90, so that's going to be just under 100. And probability of getting 3 was 270, so let's see, it's 250. 270 might be about right there. Uh, 4 was 405, so that's going to be just over. Just over. And then 5 would be 243. So if that's 250, then 243 is just under it. All right. So there you go. There's your histogram. The distribution is mounded. It is definitely mounded and has a tail to the left. So the distribution is skewed left. Okay. And you'll notice it goes sort of like this. Okay. So you got a longer tail to the left. So it's skewed left. That's not a real good color. How about some UT orange? There we go. All right. That's a little easier. Okay, so the longer tail, so it's skewed to the left. The probability of getting 3 or more heads is, well, the probability of 3 plus the probability of 4 plus the probability of 5. So that's going to be 270 over 1,024. 405 over 1,024, and 243 over 1,024. So if you add those 3 up, you get 918 over 1,024, which is approximately 0.896. All right. Now, the probability of getting at least 1 heads is, you could do it. That's the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 5. It's easier to just do 1 minus the probability of 0. Since when you add all of these up, it equals 1. So you could just subtract the probability of 0, which is 1 minus 1 over 1,024, which is 1,023 minus over 1,024, 1,023, which is approximately 0.999. Okay, and you're almost certainly going to get at least 1 heads when you flip it 5 times. Reflect. Why are the probabilities in the histogram you made in Explorer different from the probabilities given in the histogram in Part A? Well, if you look, the histogram in the Explorer was based on experimental probabilities, so there's randomness in the results. And let's also, let's see here. Probabilities in the Explorer. And let's see. One of them had 40%. And then, go back. when you flip a coin, one of them was 40% and the other one was 75%. So it's got to do with the randomness. So the histogram in the Explorer was based on experimental probabilities. So there is randomness in the results. Now, you could stop this video and take your quarter and flip it 5 times and record your results. Then flip the same quarter 5 times and check your results. And they're probably not going to be the same. Or you could flip one quarter 5 times, record those results, get another quarter and flip it 5 times and see those results. Probably would be different. For each coin, the fair coin in part A is based for which coin, the fair coin in part A or the biased coin in part B is flipping a coin 5 times and getting 5 heads more likely to occur. Well, remember the biased coin in part B, I think it had a 0.75 of heads, right? So the biased coin in part B is more likely to produce 5 heads and 5 flips, because the probability of 5 was, what was it, like 0.03 or 0.237, and for in A, the probability of 5 was 1 over 32, which is 0.031. Okay, so I mean, it's about 7 times more likely that you're going to get it with the biased coin than you are with the fair coin. Discussion. Can you definitely conclude whether a coin that results in repeated heads when flipped is fair or biased? What might make you favor one conclusion over the other? Well, you should assume the coin is fair. Assume the coin is fair so long as the result is not very unlikely. Determining when a result crosses over into being very unlikely is debatable, however. So assume the coin is fair. Now, if you do, we'll say like 10 trials, and 7 or 8 result in 5 heads, then it's highly likely that coin is biased. Okay, but experts, they can't really agree on what would constitute unbiased. Calculate all the probabilities for a given binomial experiment. Then draw a histogram of the probability distribution, observe its shape, and use it to find the specified probabilities. A binomial experiment consists of flipping a biased coin for 4 trials, where getting heads is considered a success. The coin lands heads up 40% of the time. Find the probability of getting 2 or more heads and the probability of getting fewer than 4 heads. Okay, so P this time, P is going to be 0.4. Q is going to be 1 minus 0.4, which is 0.6. Okay, So 4 choose 0 times 0.4 to the 0 times 0.6 to the 4. That would give you this first one, 0. All right, let's try that in our calculator. Menu 5, 3, and that's going to be 4, comma 0, close parentheses, times open parentheses 0.4, close parentheses, caret 0, times open parentheses 0.6, close parentheses, caret 4. And that gives you 0.1296. 0.1296. 4 choose 1, 0.4 to the first power, 0.6 to the third power. Let's see, it's 0.1296. And let's try this one here. Menu 5, 3, 4, comma 1, close parentheses, times open parentheses 0.4, close parentheses, caret 1, times open parentheses 0.6, caret 3, and that gives you 0.3456. 0.3456. 0.3456. And then 4 choose 2, 0.4, 0.6, 2, and that's going to give you 0.3456. 0.3456. 0.3456. And then 4 choose 3, 0.4 to the third power, 0.6 to the first power, and that's going to give you 0.1536. And then the fourth one is going to be 0.0256. All right, so 0 is 0.1296, so that's 0.15, 0.1296, maybe right there. 0.3456, that's almost going to be 1, 2. Those two are the same height. And then 0.15, that's going to be just barely above it. And this one here is 0.02. So if that's 0.1, that's 0.05. So 0.0256, a little bit over half. All right, so it should look, the histogram should look something like that. And if you look, what do you call it? The distribution is skewed to the right. You got a longer tail over here. The distribution is skewed to the right. Right. All right. We want to find the probability that x is greater than or equal to 2. So that's going to be the probability of 2 heads plus the probability of 3 heads plus the probability of 4 heads. And just write that off the table. 0.3456, 3456 plus 0.1536 plus 0.0256, and we can put those in our calculator. 0.3456 plus 0.1536 plus 0.0256, and that's 0.5248. So that equals 0.5248. Okay. Now, the other one was probability that x was less than 4. which is going to be the probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3. Okay? Now, if you add all of these up, that would equal 1, okay? Minus a little rounding maybe. So we could say that this is going to be 1 minus the probability of 4, okay? And so let's see here. Let me get this. I don't want to write it. That would equal 1 minus 0.0256, which is 0.9744. Okay. Not too bad. Moving right along. Your turn. A binomial experiment consists of flipping a biased coin for 4 trials, where getting tails is considered a success. The coin lands heads up 40% of the time. Find the probability of getting 2 or more tails and the probability of getting fewer than 4 tails. So P is going to be 0.4, Q is going to be 0.6. I think that's just the opposite of the last time, right? All right, so probability of 0 is going to be 0.0256. Probability of 1 would be 0.1536. Probability of 2 is 0.3456. Probability of 3 would be 0.3456 and 0.1296. So this is going to be, 4 choose 0. 0.4 to the 0, 0.6 to the 4th. This one here would be 4 choose 1, 0.4 to the 1, 0.6 to the 3. This one here would be 4 choose 2, 0.4 squared, 0.6 squared. This one here would be 4 choose 3, 0.4 to the 3rd power, 0.6 to the 1st power. And this last one would be 4 choose 4, 0.4 to the 4th, 0.6 to the 0. All right? That's where I got all of those. So let's look at this. This is 0.0256. So that's maybe half of that right there. 1 is 0.15, so that's going to be just above that. And that's slightly off. 2 is going to be 0.3456. That's just under. And then 4 is 0.12, so that's going to be about half of that right there. All right. Now, if you'll notice, this one is skewed to the left. This is skewed to this distribution is skewed left. It is skewed left. So we want to find the probability that x is greater than 2, greater than or equal to 2, which is going to be the probability of 2, plus the probability of 3, plus the probability of 4, which is 0.3456 plus 0.3456 plus 0.129. I got them right here off the table. That looks 5, 6. And that is going to equal 0.8208. And we also want to find the probability that x is less than 4. So we'll just use 1 minus the probability of 4, which is 1 minus 0.1296, which is approximately, which is about 0.8704. All right, not too bad, not too bad. What is a random variable and what makes a random variable discrete? A random variable is a variable whose value is determined by the outcome of a probability experiment. If the outcomes are distinct, such as whole numbers, the random variable is discrete. A random variable is a variable whose value is determined by the outcome of a probability experiment. If the outcomes are distinct, such as whole numbers, the random variable is discrete. How can a histogram for a probability distribution be used to calculate a cumulative probability? The probability is the sum of the areas of the bars in the histogram. The probability is the sum of the areas of the bars in the histogram. Now, let's go back here for just a second. If you add all of these, if you add all of that up, it should equal 1. Okay, we talked about that a minute ago. So the sum of the area in a histogram is 1. Okay, so the bars correspond to the values. The bars correspond to the values of the random variable that are less than or equal to a given value. What is a probability distribution for a discrete random variable? See, a probability probability distribution shows the probability and you might put in here either empirically let me put that on the next slide. Either empirically, and that was supposed to have two L's. Either empirical or theoretical associated with each possible value of the random variable. All right, now folks, empirical means what actually transpired, okay? And theoretical means what is supposed to transpire. They're not always the same. They're not always the same. Great lesson. Enjoy your evening, and I will see you in class tomorrow.